considerations regarding wrapping up our chat on establishing rationale for strengths of bronzosyluric acids and bases. I want to make one more comment on species like nitrate ion. You'll find this particularly important in organic class, because a whole lot of organic species show this property. They're looking to find out if a species exhibits resonance. You know how to play that game by way of writing Lewis pictures. If for the species in question you can write 2 or more acceptable Lewis pictures which show as the only apparent difference position of multiple bonding electron density, and you haven't violated any rules in writing these Lewis pictures, you're looking at a species which shows resonance. That leads to a hybridization consideration. Nitrate ion. We recognized, among other things, that this is a particularly weak stable base. Not only because it's composed of atoms of appreciable electronegativity, and it only has a total charge of -1, which means the actual formal charge on each peripheral oxygen only -1/3. So we're looking at a net formal charge which is not large at all for the peripheral atoms, the atoms which would engage in bond formation interaction with H+. We're also looking at a species which effectively stabilizes negative charge density by resonance. We can recognize resonance because we can rewrite this Lewis picture showing the apparent double bond either here nor here, while recognizing there is no double bond, nor is there an NO single bond in this thing. All the bonds are equivalent in length and strength. Bond order is 4/3. 3 total resonance pictures. Why is resonance an appreciable property, a significant property of this species? It's planar. So we showed with models that this will allow for all the lobes of the p orbitals for all the atoms of this species to be mutually parallel, which gives us the best possible degree of overlap of these lobes with each other to make a strong pi system. So the question to which this leads, and which I forgot to mention yesterday, is how are the peripheral atoms hybridized? Likely as not, before this question, you've only looked at hybridization considerations for central atoms. Not unusual, because that relates, of course, to species geometry. Now, hybridization peripheral atoms has nothing to do with species geometry, but it has a lot to do with species valence electron structure. How are these peripheral oxygen atoms hybridized? Well, have we not, by way of recognizing that resonance is an important property of these species, realized there's part of a pi bond at every one of these bond sites? And if an atom is going to be a participant in a pi bond, it's got to have, if it's a period 2 atom, empty p orbital space, so to speak. It cannot be hybridized in excess or beyond sp2. Because if it's sp3, all the p orbital is used in the sigma system. So we're looking for sp2 hybridization, which we also noted for the central nitrogen atom. That leads to the question, how are the peripheral oxygen atoms hybridized? Well, they too are participants in pi bond formation. So we make a statement, independent of looking at this, which suggests sp3 hybridization, or this, which suggests sp3 hybridization. By this I mean the valence electron structure for this oxygen, as well as this oxygen shown by our Lewis picture. Now this oxygen appears to be sp2 because it's associated with this pi bond. But note, an atom with non-bonding pairs, these atoms all have non-bonding pairs, bound to an atom which is sp2 hybridized, that's this atom, is also sp2. So there's a rule of the road regarding hybridization determination that you need to be familiar with, because you're going to see a number of species which exhibit this property. A simpler case, nitrite ion, generated from nitrate ion by removing one peripheral oxygen atom. How is this atom hybridized? Well, we recognize this too shows resonance. These hetero bond lengths and strengths are equal. Shorter, stronger single bond. Longer, weaker double bond. Bond order 1.5. Which means this oxygen atom is also participating in pi bond formation with the central nitrogen atom. Has this atom got non-bonding electron density? Yes. Is it bonded to an atom which is sp2 hybridized? Yes. So this too is sp2 hybridized. That's the game. Now, a couple final cases. Perchloric acid, which in brief we talked about yesterday, as an acid which we find to be the strongest one listed in our acid-base table, as a consequence particularly of the fact that this thing, after it loses H+, has got 4 peripheral oxo-oxygen atoms, which effectively stabilize negative charge density by induction. Here, with the 4 peripheral oxo-oxygen atoms, you wind up with a formal charge of only -1/4 on each peripheral oxygen atom. Well, that's already smaller than -1/3 for nitrate ion. So even though nitrate ion is a very stable, very unreactive base, the perchlorate ion is even more stable. So let's take a look at perchloric acid, pardon me, and compare its strength to that of perbromic acid. And I don't care about names if I haven't written this stuff down. Well, if I want to write the Lewis picture for the conjugate base of the perbromic acid molecule, all I got to do is take these pictures, erase the chlorine central atom, put it in with bromine. So I'm looking at 2 anions, which are each tetrahedral.
Is on the left picture, is that top oxygen supposed to be double bonded or is it non-bonded pair?
No, here. Here, I've shown all the oxygens as being singly bonded. Because this shows maximum formal charge distribution. And if we imagine then that by multiple bond formation between peripheral oxygen and chlorine, we can go all the way to this. That reduces formal charge on this oxygen from -1 to 0, and the chlorine from +3 to +2. Put another double bond here. Now this oxygen becomes formal charge 0. Chlorine's now formal charge reduced to +1. And if I do this one more time, I wind up with this. Of course, I'm not going to go to 4 double bonds, because that's going to wind up putting the minus charge on chlorine, and that's not as electronically suitable as having the minus charge on oxygen, because oxygen is more electronegative than chlorine. So we stop at this. Okay? And again, one of the implications of this is resonance. Now, we argued resonance is a property of a species like this, but not as good or strong a property as it is for something like nitrate ion. Because this thing is not... What? It's not planar. This is what? Tetrahedral. Nevertheless, because of all these peripheral oxygen atoms, coupled with a central atom that's also of appreciable electronegativity, we wind up with quite effective stabilization of the single unit of minus charge which the ion possesses. Now, difference in acid strength between these two. I should think at a glance we'd recognize that the acid strengths of these, if they are different, aren't going to be significantly different. They're both very strong acids. But studies show that this one is a little bit stronger. Ka for this is a huge number, and bigger than Ka for this, which is also a huge number. Not a big difference, but this one is somewhat stronger. Well, can we cook up an explanation for this? Keep in mind, if I replace this with a bromine atom, I'm looking at a species which has got the same central atom hybridization, the same geometry, the same formal charge distribution. And bromine is not much lower in electronegativity than chlorine. The values are 3.0 for chlorine, 3.1 in some tables, and 2.8 for bromine. So not a big difference. But which of these, I'll put the bromine in there, which of these ions will be larger? Well, everything's the same size except the central atoms. And bromine compares how to chlorine size-wise? Bigger. So this is the bigger ion. Point. Well, let's leave the bromine there. If for this ion, resonance is just as effective as it is for this ion, since this is bigger, I should expect a greater dilution of negative charge density here, even than what is shown by this. That would make this the weaker base. That would make this the stronger acid. But that's not the fact. This is the stronger acid. So what we're seeing here is that greater electronegativity of the central atom, even though it's not much greater, plus PMO. Why should PMO be more important for this than it is for this? Remember how this PMO business operates? The bigger the atoms, the further from the nucleus of the atom when it's involved in a bond is the bonding electron density. That makes bonding electron density less stable or more stable when you get it further from the nucleus. Less stable. Well then, we can argue that we should expect, because of better PMO for this, because chlorine and oxygen are closer in size than bromine and oxygen. So I should expect a somewhat better pi system here, somewhat more effective resonance here. And that, of course, fits the facts. But keep in mind, because students have noticed this, so we should point it out. When we've talked about the difference in acid strength of HCl and HBr, then HBr is stronger. That's interesting. Here, perchloric acid with chlorine central atom is somewhat stronger than perbromic acid with bromine central atom. But here, HBr is stronger. What's the difference? Or we can say, for these two anions, why is charge to size ratio more important than for the factors which we've considered here?
Because as a whole, the HOCl3 and PR3 are basically the same size.
They're pretty close in size, aren't they?
Yeah, so
that's correct.
doesn't matter much.
Why should we realize that the size difference between these two is only slight, whereas the size difference between these two is substantial? You realize this has to be the case? Let's play a game. Chlorine atom. Bromine atom. Big difference in size. Okay? So let's say area. Because bonding interactions, I think, depend more on an area consideration. When you size up charge density, if you ever do this, I would suggest that you do it as a ratio of total charge to surface area, not volume. Because bond interactions involve valence electrons, not something that's inside the atom and getting close to the nucleus. So let's say area BR equals twice A area for chlorine. A equals area. All right? So here are the size ratios 2 to 1. Now let's put oxygen atoms on these things. To make the arithmetic as simple as possible, let's say A area chlorine equals twice A area oxygen. All right? So what have I shown? With ball models for atoms, I've shown a very crude representation of this, the perbromate ion, versus this, the perchlorate ion. Remember, chlorine, bromine alone, or bromide ion, chloride ion alone, area ratio is 2 to 1. That has a big impact on charge to size ratio. Makes it much smaller for the bromide ion than it is for chloride ion. What have we done to the size ratio when we played this game? Well, what's the size of this thing? This is chlorine, which is 2 oxygen areas, right? Plus 1, 2, 3, 4 more. So the total area of this in terms of oxygen is 6 oxygen areas. All right? What's this? Well, we got 1, 2, 3, 4 oxygens. And the bromine counts as how many oxygens? 4. What's the ratio now? 8 to 6, 4 to 3. Whereas here, 2 to 1. Not much difference in size now.
Don't the anions expand a little bit too? Does that have anything to do with it?
Didn't hear you.
Does the fact that the anions expand,
Expand?
yeah, the chlorine and bromine, when they pick up electrons, they increase in size, right?
Sure.
So does that have anything to do with it either?
Well, my expectation is that if I take the ratio of size of a chlorine atom, a bromine atom to a chlorine atom, and compare that to the ratio of size of a bromide ion to a chloride ion. Is that what you're asking about?
Yeah.
I'd expect the bromide ion chloride ion ratio is a little bigger, or at least bigger. Okay, I'm just making this up so that we can recognize what you pointed out. The more peripheral atoms you add, the lower becomes the difference in size. So size difference here, not nearly as important as size difference here when we're dealing with monatomic species. All right? Now then, enough on Bronsted acidity of molecules. One other type of acid, Bronsted acid, whose strength we've paid attention to early on, at least for arithmetic, because a couple of these Bronsted acids are contained in our acid-base table. Hydrated metal ions. What can we say about strength rationalization for hydrated metal ions? First, all these factors that we've summed up for all these molecule considerations, they don't apply here. When we're talking about Bronsted acidity of hydrated metal ions, we have to pay attention strictly to properties of the metal ion itself. Because in each case, the H plus source is a water molecule that's stuck to this metal ion. So the source of the H plus for hydrated metal ion is always the same. It's always a hydrated water molecule. So, what properties of the metal ion itself and these metal ion hydrates might we pay attention to get at acid strength of a hydrated metal ion? To get at that, we got to first ask a question. Is the metal ion noble gas structure, or is it not noble gas structure? Well, if you, for example, look at our acid-base table, or if you reflect on stuff you've done in 46 laboratory. I've written here, how about aluminum ion hydrated versus hydrated magnesium ion? If you look at the information in our acid-base table, or just pay attention to the work that you've done in 46L, assignment number 4, what'd you find out about the difference in acid strengths of these two? Which one is by far the stronger acid? Ka this, 1.4 times 10 to minus 5. Very close to Ka for acetic acid. Ka this, I don't remember what it is, but it's in the table. It's not a big value. I think it's on the order of 10 to the minus 12. Take a look. You got the table. Four times 10 to minus 12? Okay. Big difference in acid strengths. And remember, if you will, we've noted that species like sodium ion and potassium ion do not even form defined hydrates. So making water solutions of sodium ion and potassium ion does not result in any impact on pH at all. What's that mean? That means that the acid strength of a hydrated metal ion, provided that the hydrated metal ion has this property. What's this property? Noble gas structure. Is aluminum ion a noble gas structure ion? Aluminum ion is aluminum plus 3. Is that a noble gas structure? What's it like? Neon. How about magnesium ion?
Also neon.
Neon. How about sodium ion? Neon. How about calcium ion?
Argon.
Argon. Those are all noble gas structure ions. All we have to do to establish a rationale for differences in Bronsted strength, acid strengths of hydrated metal ions, which are noble gas structure, is pay attention to charge density of that metal ion. Aluminum ion versus, say, magnesium ion. Water molecule. Water molecule. What is the difference in Coulombic interactions between these two hydrated metal ions? Of course, the hydrate's got 6 water molecules wrapped around it, but I'm going to draw 6 water molecules around these ions because then we're going to have a mess for a picture. Okay? Here, the bond interaction is stronger because this has got a charge of 3 plus, and this is a smaller ion. So the charge to size ratio for aluminum ion is considerably greater than the charge to size ratio for magnesium ion. So I got a shorter, stronger bond here. And I also have hydrogen atoms on this hydrated water molecule, which are now closer to this site of positive charge. This distance here is shorter than this distance here. My picture, unfortunately, doesn't do a very good job of showing that. There's a better illustration in the notes. What we're talking about now begins on page 2337. So I have a shorter, stronger bond interaction here. Means aluminum ion is hydrated more tightly, if you will, than magnesium ion. But let's get at acid strength. Here I'm bringing the H atoms on a hydrated water molecule closer to the site of positive charge, and this positive charge is greater than it is here. So here I have a greater repulsion between the partially positive end of a water dipole and the metal ion. That makes the hydrogen-oxygen bond easier to break. It weakens the hydrogen-oxygen bond more so than I weaken the hydrogen-oxygen bond here. Well, the greater degree to which I weaken the hydrogen-oxygen bond, the more easily that hydrogen-oxygen bond is ruptured, and the more easily H plus swims off into solution. Point: if I have hydrated metal ions, which are noble gas structure, all I need to do is pay attention to charge to size ratio of the metal ion. And then I can say something meaningful about the strength of that hydrated metal ion. You may recall on exam 2, I asked you a question about these ions from an acid strength standpoint. Remember what I asked you? Or exam 2 already ancient history. Forgot about that. We put that underneath the pyramid. Never again to be examined until the mummy comes forth and brings this out for us to look at again. These metal ion hydrates have Ka values which are about the same. And I asked for a rationale. Well, what's the difference? This is a +2 metal ion. This is a +3 metal ion. These are each noble gas structure metal ions. This metal ion, noble gas structure, is the same as that of what? Helium. But this metal ion noble gas structure is the same as that of neon. So when I'm looking to determine a charge to size ratio, 2 plus to say He versus 3 plus to Ne, and I tell you that Ka values for these are about the same, what can you tell me about these ratios? They different? Much different? Or are they about the same? Got to be about the same. Enough said. Now then, let's get to some fun stuff. Or I should say more fun stuff. Ka, this stuff, 4.0 times 10 to minus 3. Just pulling that right off the acid-base table. You folks, if my memory's right, you wrapped up your 46L work, or are wrapping it up this week, correct? How many of you got to assignment 10? Right. You doing the acid strength determination on hydrated iron +3? What'd you find out about it?
That it's a stronger acid
Then what?
than copper.
Stronger acid than copper ion. How does the strength of hydrated copper ion compare to aluminum ion? Let's put this up there. How does Ka this compare to 1.4 times 10 to minus 5? 1.4 times 10 to minus 5 is Ka for hydrated aluminum ion. Of these three, which is the weakest acid? Well, maybe my memory's wrong. Did I give you Ka for this? Is that on our acid, this in our acid-base table? Take a look. I don't know if that's in the acid-base table. I think it's in the lab manual. Okay, my fault. This one is weaker. All right, let's put this in here and make the comparison more meaningful. All right, now we got it. I made a mistake on my comment on the acid strength of copper. But, what can you tell me about the size of a copper ion all by itself, not hydrated, versus magnesium ion all by itself? Also, what can you tell me about the size of aluminum ion all by itself versus that of iron plus 3 all by itself? These two, compared to each other, these two compared to each other. Sizes. Which of these do you expect to be smaller by far? Aluminum plus 3, this is isoelectronic with neon, and it's even a good deal smaller than neon. Hey, this thing's got a neon configuration. What's configuration for this thing?
3D5.
Argon 3D5. This has got a whole lot more electrons than this thing. This is neon. This is argon 3D5. As soon as you see energy level number 3 electrons as part of the valence configuration for something, you can well expect to be a good deal larger than anything which hasn't got any valence electrons beyond energy level number 2. What can you tell me about these two? Electron configuration 1. What's this thing?
Argon 3D10 force 1.
Argon what?
3D10 force 1. Oh, minus electron.
What is it?
3D9.
3D9. What's this thing? This is neon again. So, as isolated ions, ions all by themselves, not hydrated, I can well expect this to be a lot bigger ion than this, and this to be a lot bigger ion than this. So, what we are seeing is that if I have a hydrated metal ion, which is not noble gas structure, you can forget the simple Coulomb argument based on charge to size density of the metal ion itself. It won't work, because this ion is a lot bigger than this ion, yet the hydrate of this is a heck of a lot stronger acid than the hydrate of this. Same follows here. You found the same thing in laboratory about magnesium ion hydrated. That's a stronger acid than the zinc ion hydrated, pardon me. Hydrated zinc ion is a stronger acid than hydrated magnesium ion. What information did you find in lab to confirm that? This Ka, this is bigger than Ka. This. I like to pick at this lab stuff. What did you do in lab to support the conclusion that hydrated zinc ion is a stronger Bronsted acid than hydrated magnesium ion? What did you do in lab to reach this conclusion?
Zinc reaction with ammonia or magnesium metal.
Oh, yes, it does. Anything else? Well, the first reactions you ran with each of these ions was to treat them with hydroxide ion, and found out they each make hydroxide gel precipitates. Remember that? Plus hydroxide ion makes this. And plus hydroxide ion makes this. Oh. Okay so far? What did you do next after you made these hydroxide precipitates?
Added more hydroxide
To find out what?
to see if the precipitate dissolves.
See if the precipitate dissolves. See if the precipitates are showing what property? Amphoterism, right? Okay. Which one showed itself to be amphoteric? Which one dissolved by treatment with excess hydroxide ion?
Zinc.
Yeah. Well then, this has got to be a stronger acid than this, which supports the conclusion that this is derived from a stronger acid than this. Right? You had evidence to confirm that hydrated zinc ion is a stronger acid than hydrated magnesium ion. But the fun part of this is why. How can these metal ions, which are considerably larger than the noble gas structure metal ions of the same charge, be a good deal stronger acid? What's going on here? Back to these terms, which we paid attention to when we're trying to establish a basis for rationalizing trends in atomic size. There's our hydrating agent. Got non-bonding electron pairs, which become, one of these becomes a bonding pair, right? When a water molecule reacts with something like iron plus 3, we form a strong coordinate covalent bond. We developed this model at the first time at the end of chapter 19, when we talked about Lewis acid, Lewis base chemistry, where the Lewis acid supplies an empty valence orbital and the Lewis base supplies a non-bonding pair, which on bond formation interaction becomes a bonding pair. Okay so far? These electrons are from what energy level? Non-bonding electron pairs on oxygen. Energy level number 2. From N equals 2. What do you remember when we talked about this kind of stuff for this size trend business? About Z effective and penetration ability of electrons from energy level number 2. What kind of electrons would these be from a hybridization standpoint? How would you argue this oxygen atom to be hybridized? sp3. So only 25% S character, but these S electrons are from energy level number 2. What did we recognize about the penetration ability of S electrons compared to PDF? S best. They're the least effectively shielded. Best penetrators. And N equals 2 S electrons are dandy penetrators. They're really close to the nucleus, aren't they? Well, imagine what happens When these electrons derived from energy level number 2, which by default makes them fairly good penetrators, make a bond formation interaction with iron plus 3 that's got 3d electrons. And how many protons in the nucleus? 26. Versus aluminum with 13 protons in the nucleus. Well, if these electrons, which become bonding electrons when the water molecule glues on iron plus 3, if these electrons have this penetrating ability that we have suggested that they may have, they penetrate through these poorly shielding 3d5 electrons. And electrons from energy level number 3, which are part of the argon configuration, which are not nearly as effective shielders as electrons from energy level number 2. These electrons are approaching a nucleus which has got 26 protons in it versus only 13 for aluminum ion. What's that going to do to the strength of this coordinate covalent bond for water stuck on iron plus 3? You'd make it daggone strong. It's going to bring those hydrogen atoms on the water molecule that's stuck on iron plus 3 close to a nucleus that's got a lot more protons in it than that for aluminum. Right? Is that going to give me a species which is going to more easily rupture an OH bond heterolytically and kick H plus in the solution and behave as a stronger acid? You betcha. Fancy argument. Why do I use it? It fits the facts. That's why I use it. And frankly, I haven't seen a better argument. As fanciful as it may seem. But it fits the facts and it follows from this stuff which we've already talked about. Enough said on that. Now then, chapter 23. If you take a look at page 2339, you'll see a topic considered called polarization. I'm not going to consider that. I think there's enough holes in the polarization argument that it's not worthy of being considered at this stage of the game. So we're going to go past the polarization stuff, and you'll see on 2341, ionic versus covalent character of binary A family metal compounds, thermodynamics of solution formation, and how we can decide when forming a solution of a metal ion will be entropy driven or enthalpy driven. I think we've done enough with that kind of stuff, so I'm going to go past that too. And then when we get to section 23.9 on page 2345, descriptive chemistry of A family metals, you can read that. It's pretty much an account of how these metals behave without much explanation involved. So we'll go all the way to 2352, metallurgy. Now I expect you've all heard this term. If I asked you to give me a working definition of the science known as metallurgy, what would you say? Any idea? If you look up metallurgy in a dictionary, you got any idea what you'll find? you'll find something that reads like this. The science of extracting and purifying, fill in the blank from ores which contain such. What are we going to put in the blank? What do you put in the blank? How about metals? Nothing fancy about that, is there? Metallurgy is principally what specific science? What do you want to put in this blank? How about that? Chemistry. Oh boy. All right. So at the minimum, I should think this definition gives you an idea of why we will discuss metallurgy, at least in brief. There are 3 steps to the metallurgical procedure. They're outlined on page 2352. Involves 3 principal steps. Roman numerum, yeah, 1, I, okay. Let me wrap this up in print. Preliminary treatment. What this refers to is doing a geological survey, for starters. We send geologists about, or mineralogists about, to do some investigations on Earth's crust. What are we looking for? We're looking for ores, natural mineral deposits, which we find in Earth's crust, that are rich in metal ion components in which we are interested. What kind of metals do you think we're often looking for? Or metal ions?
Iron.
Iron, you betcha. Make a lot of stuff out of iron. Aluminum, copper, zinc, you name it. This is how we get these stuffs. Chromium, nickel, you bet. Okay? So we're looking for ores which contain these metals, usually as oxidized species, as metal ions. Okay? Preliminary treatment. To obtain and concentrate ore samples. Which contain the metal, usually as a metal ion. Of interest. Okay? Now this, part of this may be done at the place that makes the metal. Have you heard of Reynolds Aluminum? Alcoa Aluminum? Heard of any of these places? Okay. So, if you're making aluminum, aluminum's too reactive to ever find as base metal aluminum. You'll always find it as an ore called bauxite, or some variants thereof. Bauxite, mineralogist's name for aluminum oxide, Al2O3. Concentrate this stuff, put it on freight cars, whatever, and ship it to the aluminum making plant. Alcoa or Reynolds, wherever it might be. Okay? Then we go to step 2. What's this stand for? Reduction. obtain base metal. So the folks at Reynolds, whatever have you, they get all this aluminum oxide, and then they reduce the aluminum oxide to get aluminum. That's discussed in here. It's good chemistry, because, I mean, if nothing else, it's redox chemistry, fundamental redox chemistry. Okay, and then at last, if necessary, refine, which means purify, if necessary. In the notes, there's a rather detailed explanation of how aluminum is ultimately obtained, prepared at places like Reynolds Aluminum and Alco and stuff like that. But I'm going to jump to one metallurgical consideration. Involving purification, step 3. Consider X, for example, of 3 for copper. Which is done by electrolysis. To which we'll add this note. Copper after reduction to get the copper is often found to be contaminated by trace amounts of other TMs. What are TMs?
Transition metals.
Transition metals. All right. So, the folks at the copper purification plant make a big electrolysis cell, big vat. And from the impure copper, they form an anode, just a big copper bar. An anode which is not pure copper because it's got these other transition metals in there as contaminants. In this same electrolysis bath, they use another big copper strip or bar as a cathode. But this copper strip is pure, already purified by this procedure previously. All right? And now, we connect the anode to the cathode with wire and a power source. Because what we're going to do is to pump electricity through this system, the electrolysis procedure. Well, that means we got to have stuff in solution which can carry current. We got to have ions in solution. my checking on this system in operation indicates they use copper sulfate as the electrolyte. You might recall when we talked about making an electrochemical cell which gives us usable electrical energy from a sample of, copper and zinc and copper ion and zinc ion. We use copper sulfate and zinc sulfate. So they use copper sulfate. So you got this big water solution of copper sulfate. Now, after this thing is put together, power source with voltage set just right to all oxidize copper at the anode, i.e. M for metals. Let's get this out of the way. Less reactive than copper will not be oxidized. Okay so far? Now then, what metals might we expect to find to be trace impurities in our copper anode, which are transition metals, and which are more reactive than copper? Zinc, nickel, cobalt as possibilities. What happens to these metals that are more reactive than copper when we turn on the power and this bar begins to dissolve by oxidation? Because what's happening at this bar principally is this. Chemistry we've seen before. If this happens at the anode, what will happen to zinc and nickel and cobalt and other transition metal impurities, all of which are more reactive than copper? When I say more reactive, what do you think I'm telling you about the ability of these other metals to be oxidized? Are these more easily oxidized, these other metals? Sure. If I got enough voltage applied to this anode to oxidize copper, then I'm also going to oxidize all the metals which are more reactive than copper. All right? So, Cu and all M's more reactive than Cu go into solution as hydrated metal ions. Not surprising. Now, recognize that if I've got the voltage set just right, minimum required to oxidize copper at the anode, then at the cathode, I've got to have the same voltage. I can't apply across two electrodes different voltages. So I have to recognize that at cathode, voltage is also just right to reduce copper ion to copper. So I'm transferring copper from the anode to the cathode by this procedure. But remember, the cathode is pure copper. Will I continue to will I also contaminate the cathode by this process? Well, remember, the metal ions which I put in solution, beside copper ion, are derived from metals that are stronger reducers, more readily oxidized than copper. Well, what about these metal ions like zinc ion? Or nickel ion or cobalt ion. Am I going to reduce this at the cathode? If you remember from the from the half reaction table, hydrated zinc ion, hydrated copper ion, which is the stronger oxidizer? These other metal ions like zinc ion have been derived from metals that are more easily oxidized than copper. Okay, so far? What does that tell me about the strength of their oxidized form as oxidizers? How does the oxidizing strength of this compare to the oxidizing strength of hydrated copper ion? We did this in chapter 22. Which one is the better oxidizer, hydrated copper ion or this thing? Hydrated copper ion. Remember, of the metals oxidized, copper is the most difficult to oxidize. The other metals are more easily oxidized because they're stronger reducers. That means their hydrated ions are poorer oxidizers. They're more difficult to reduce. I got this voltage set right to reduce copper ion, which is the easiest thing in solution to reduce. Because this thing is a stronger oxidizer than any of these other hydrated metal ions I make. Well, I'm only reducing this then. So I keep putting more copper on my copper cathode, which means I don't contaminate this cathode by redepositing other metals. I don't have the voltage high enough to reduce these other metal ions. They're more difficult to reduce than hydrated copper ion. So that's why I keep making this thing a bigger and bigger pure sample of copper. And what the folks do at the copper plant is after this bar gets so big, they take it out and put it in a small bar and keep on going. They keep turning this pure sample of copper at a given size to a much larger sample of copper and keep replacing, take out the large sample of copper, put a small sample, the large sample of copper by this process. Now comes the fun part. Because we also recognize that copper will originally have been contaminated with metals that are less reactive. Not just more reactive, but also less reactive. So what happens to these metals that are less reactive? Hey, sludge forms as anode disintegrates. Sludge is composed of metals less reactive than copper. Nothing fancy about that. These metals, which deposit as a sludge, are more difficult to oxidize than copper, and I haven't got the voltage high enough to oxidize those. I don't want to oxidize those metals. So, the fun part is, what would you say if Mom and Dad came to you on your birthday and said, for this birthday, I'm going to reward you with a bag of sludge. Would you like to have a bag of sludge as a present? Would you like to have a bag of this sludge as a present? What is this sludge? This sludge is a bunch of metals which are more difficult to oxidize than copper. What are these metals?
Everything else.
What are these everything else?
Zinc, magnesium. easier.
Oh no, those are easier to oxidize than copper. They're in solution swimming around as metal ions. I'm talking about this sludge. These are the metals which didn't get oxidized. I haven't got the current, the voltage high enough to oxidize these metals. They fall down as sludge. So I'm going to pick up this sludge, put it in a bag and say, here, that's your birthday present. Do you want this sludge?
I do.
What is this sludge composed of? It's composed of metals which are more difficult to oxidize than copper. They're less reactive than copper. Can you name me some of these metals? How about silver? How about gold? How about platinum? You're damn right you want this sludge. In fact, what's very interesting about this copper purification procedure is, if the information I've read, if it's correct, the sludge more than pays for the copper refining process itself. Because when they collect this gold and silver and platinum, they sell it for a lot of money. How about that? We'll pick it up from this point tomorrow.